Based on some of the discussion I saw on Piazza, I thought it might be useful to do a couple linear momentum problems, but include energy in them as a supplement to allow me a chance to talk about some ideas. So look at actually 3 problems related to work energy and momentum, 2 related to work energy and momentum, 1 which is more a momentum problem, and examine what's happening to the motion. Again, as much as possible, we're trying to get you to think about these problems conceptually, and conceptually you've got to kind of recognize what things are important and what things are not, and it's not always intuitively obvious. So let's start out with a relatively simple problem. This is something that you'll see at the introductory part of the course, where you have a golf ball being hit, say a 40-gram golf ball hit over an interval of 3 milliseconds by a club. The ball leaves with a velocity of 40 meters per second at an angle of 35 degrees. Neglect the ball's weight while it's struck. So I'm going to go back to that final sort of sentence, but really kind of important to sort of recognize that often we do neglect weight in these questions. You're asked to find the average impulsive force exerted on the ball and the momentum of the ball 1.4 seconds after it leaves the club face. Draw the momentum and impulse diagram after the ball as it's struck. Apply the principle of impulse and momentum to determine the average impulsive force. Use kinematic relationships to determine the velocity of the ball after 1.4 seconds. Then calculate the linear momentum. All right, so it's, again, as much as possible, you're trying to sort of solve through a problem, and you know that it is going to be one that you have to look at impulse momentum because you've been told impulse momentum. So I start out and I drew the impulse momentum diagram, and if I do that, I have to sort of recognize that the ball starts at rest, so it has a momentum of 0. I have weight forces acting on it and normal forces, and for now I'm just going to assume that they are 0. I'll go back to this assumption afterwards because I think this is kind of useful to sort of look at. I'm given a force is applied for 3 milliseconds, so that's my impulse, and my final result is a ball that's going at 40 meters per second at an angle of 35 degrees. So if I do that, I can use the principle of impulse momentum. So 35 degrees, mv naught, sum of all of the forces, and in this case, I'm just looking at the impulse force, dt mv1. So mv1 is the immediate velocity of the ball after the club has hit it for that 3 milliseconds. The average impulsive force can be treated as a constant, so we'll assume that it doesn't change over those 3 milliseconds. I mean, it's a short period of time. That's usually a pretty good assumption. And we know that velocity is not is equal to 0. So substitute in terms, constant average 0.003 seconds, 0. And then we have mass times velocity. Substitute in terms, and you get 533 newtons at 35 degrees. Super. That's not hard, it just sort of makes sense. After impact, it's a projectile motion problem. So I know that the x velocities will not change, so it's v1 cos 35 degrees, and it's 40 cos 35 or 32.8 meters per second. For the second part, I know it's projectile motion, and so there's an acceleration terms that comes from gravity, and that's v1y minus gt equals 40 times 30 sine of 35 degrees minus 9.81 times 1.4 seconds, or a final velocity of 9.2 meters per second. So velocity 2 is 32.8 I plus 9.21 j meters per second. And what I'm going to do then is I'm going to calculate the linear momentum, L equals mv, so L mv. Just have to put in mass, multiply it across, and I get 1.3 newton seconds, at 15.7 degrees. Now, what about that weight of the ball? We neglected it at the very beginning, but let's calculate it. So I've got mass of the ball times gravity, so that's weight, times delta t, and I'll get 0.0012 newton seconds. And in the end, it's about 0.09% of the impulse. So as far as my calculation error, from not including that, it is minuscule and it's not relevant to the calculations I've done. It won't affect this 1.36. And so this is how you have to sort of think about these problems. And this is why often we do neglect this particular term. So let's try a little bit more complex problem. So here's a problem where I have a person who is sliding down a ramp. The ramp happens to be on wheels. The person has a mass of 60 kilos. The cart has a mass of 40 kilos, and its angle is 26 degrees. The length that the person slides down this ramp is given as 3.5 meters, and I was very good on this problem, and I put in my XY coordinate system. And so you're asked to find the velocity of both the person and the cart when the person slides down to the bottom of the frictionless incline. Now, if I look at these two green arrows, that's what I expect to happen. I expect that the person will slide down, and as that person is sliding down, the cart is going to go off to the right. And so it's a positive direction for the person, positive direction for the cart. It's a negative X and Y for the person. So again, I know that as things happen, that there has to be a reaction, and the momentum often takes care of that. And so this is kind of the intuition you start to develop as you deal with these problems. As usual, ignore the mass of the wheels on which the cart rolls and any friction in the bearings. So, you know, it's again dynamics. We don't deal with the truly complex stuff yet. If you go on to third, fourth year mechanical, you will see some of this stuff as part of your problems. So really simple, I could draw a basic free body diagram. I've got weight of the person, I've got weight of the cart, I've got the angle, and I have the direction over which this is occurring. Person goes from position 1 to position 2. I know that the momentum in the x direction is conserved, so MAVAX1 plus MBVVX1 equals MAVX2 plus MBVX2. Okay. There's no friction work, so it's all gravitational potential and kinetic energy. At position 1, it's going to be kinetic energy of the person and kinetic energy of the cart. As well, I'm going to define a datum down here, and V1 equals MAGL sine theta. So that's the height of the person at position 1. Again, I've defined my datum at the bottom of the motion of the person, and so it is going to be 1/2 MAVA2 squared plus 1/2 MBVB2 squared. V2 is equal to 0 because there's no, or it's at the datum, and so the gravitational potential is 0 at that point. Datum is aligned with 2. I can define a unit vector which is going to follow along with that. That goes as E sub t, and E sub t from the geometry, I mean it's unit vector, so it has unit length 1 minus cos theta I minus sine theta j. And velocity of A with respect to B, the person sliding down, is going to be in the tangent ET or tangential direction. So I can write velocity of A is equal to velocity of B in the x direction minus velocity of A with respect to B cos theta. And there is no y velocity associated with B, so it's just going to be VA with respect to B sine theta in the j direction. I know this is negative because, again, my coordinate system is given this way, and the person is sort of going this way and this way for a final velocity here. And the initial kinetic energy is 0 because the system starts from rest. So it's all gravitational potential that drives it. So I have from that velocity of A, which is equal to velocity of Vx minus VAB cos theta in the I direction minus VAB sine theta in the j direction. I can also write that as VBx minus VAB2 cos theta, VAB2 sine theta j. So just everything's in the x direction in this case. So if I draw out my triangle, I know that velocity of B is horizontal. I know the direction velocity of A with respect to B, 2. These are all at the second stage. And velocity of A to fill out my triangle is going to look like this. So I can write that as a cosine law, and I've done that here. VAB2 squared equals VBX2 plus VAB squared, VBX2, VAB2 cos theta, theta right here. So VB2 squared equals VBX2. Subbing into the equations, I have my potential energy and my momentum expressions here. And so all of this is all together. There you go. And all my unknowns are those two right there, velocity of A with respect to B2, velocity of B x2. And I can substitute and solve for those terms. And as I expected, VBx, VB2, is a positive value moving to the right, and VAB2 is a negative value moving down and to the left. So final example, looking at a person on a swing. The system starts from rest at a theta naught of 70 degrees, and find the velocities of the trolley. This is the trolley over here. And the rider at theta equals 0. So the person is going to swing through and end up down here. Neglect the mass of the cable and treat the person in the seat as a single person. Okay. So if you do that, I can sort of expect again sort of for the motion to occur in this way. That is that the trolley at B, as the person swings to the left, the trolley will move to the right. Again, this is the type of intuition you're going to start to develop. Mass A is given as 45 kilos, mass B is 9 kilos. So I also kind of know that the velocities are going to be related to each other by a factor of 5. Momentum is going to be conserved. So initial momentum equals final momentum of the system. So I have A and B in the terms. Work energy, there's no friction. I've assumed that there's no friction associated with this. And I have the weight and the normal force acting like so. I, as usual, should draw this at the very beginning of the problem, but my x, y, and my datum are at the top. I can create any datum that I want. This will not change the problem, but I've chosen a datum so that I don't have to consider gravitational potential energy of the trolley at B. So when I'm starting out this problem, I'm looking at a problem which I've sort of simplified here. There's the swing, there's the trolley, and there's the length. And if I do that, I have T1 of the system, which is 1/2 MAV1 squared and 1/2 MBVB1 squared. I have V1, which is minus MAGL cos theta naught. And at the second stage, I have T2, which is the final kinetic energy of the person and the trolley. I also have the final potential energy, which is going to drop to the low point because this is length L. I also know that at the end of this, first of all, it starts from rest. And so this is sort of the relationship. T2 plus V2 equals V1. So I also know right away that this is going to move to the right if this is moving to the left. And this is one of the things, the type of intuition you're going to have to develop as you solve these problems. It's physics plus math, and that's one of the challenges in MIE 100. I've defined again my datum up here, and so this is why these terms go as minus MAGL cos theta naught and minus MAGL. Based on all of this, I know that the velocity is going to be negative. My datum is defined here, x, minus VA2, and it's all in the x direction. Here, the trolley is constrained to move in the x direction, so VB2, and it's moving to the right, and it's positive. So my initial momentum is 0 because VA1, VB1 are both 0. And so 0 equals the final momentum of the system, and that is just going to be L1A, or L2A, excuse me, and L2B. So I kind of see what I expect, that the two velocities, in order for momentum to be conserved, are going to be opposite. I also kind of know, and I'm kind of looking at the ratio, that it's going to be a factor 5 between the two, 45 kilograms to 9 kilograms. I also have here T2, and I have V2. And over here, I have V1, and I know that T1 is equal to 0 up there. So if I solve through for all the terms, I only have two unknowns, VA2 and VB2. And so I'll get minus 3.15 meters per second in the I direction, negative because it's moving to the left, and VB2, which is 15.73 meters per second, moving to the right. There are a couple complex examples. The golf ball problem was there just because I have had a couple questions that I've seen on the course Piazza that I thought it would be worthwhile talking about what happens to weight. But most interesting about this particular problem is looking at work energy and linear momentum, and particularly in the two problems that I did at the end of this video. How do you deal with sort of knowing what that direction is at the end? Thank you very much, and